Students, welcome to the class of digital signal processing. Without doing any further delay, the topic for today is property of DFT. And like other chapters, here I will be covering the property, the proof one by one. Thereafter, we will do only a few questions of numericals that is on circular convolution, linear convolution of DFT, because we need to do the effective portion. Okay, now let's get started with this. So properties of DFT, like every other, the first one here is linearity. So linearity property, very quickly, the way to write, start with if x1, if DFT of x1n is x1k and DFT of x2n is x2k, then the linearity property says that if you combine these two with, here you will put a then DFT of a into x1n, a into x1n plus b into x2n will be given as a into capital X1k plus b into capital X2k. Now, how to prove this? Very, very easy. Just go on with the LHS. This is your left hand side, right? So the proof is going to be this way. First, right? This is DFT of this portion. This full portion, you need to take out the DFT. A x1n plus b x2n. Write the formula for DFT over here. The formula for DFT is n equals to 0 to capital N minus 1. So this is going to be a into x1n plus b into x2n e to the power of minus j 2 pi k n by n. Fine. Now separate these two. So n equals to 0 to capital N minus 1, a x1n e to the power minus j 2 pi k n by n plus b x2n e to the power minus j 2 pi k n by n. Now here also n equals to 0 to n minus 1. Next, take out the scalar or the constants. So this is a, this is n equals to 0 to n minus 1, xn e to the power minus j 2 pi k n by n. This side it will be b, n is equals to 0 to n minus 1, x2n e to the power minus j 2 pi k n by n. Now this is what? This is the DFT of x1n and this is the DFT of x2n. So DFT of x1n, we have already assumed it is given as x1k. On the top it was given and this one was given as x2k. This is how you prove it. Fine. Now the next property. The next property is the periodicity property. So for the periodicity property, remember that the signal xn is periodic with capital N, and also the discrete Fourier transform of xn, that is xk, is periodic with n. So both k and n are periodic. Periodicity. Sorry. So what does the periodicity property says? That if a sequence x of n, so if xn is periodic with periodicity of n samples, then discrete Fourier transform, then DFT of Xn, DFT of Xn, that is Xk. Xk is also periodic with Xk is also periodic with the same periodicity, with periodicity of n samples. Now let us see this, how to do it. So small xn is periodic with xn plus n, and capital Xk is also periodic with capital X k plus n. So if this, then this. So if I take out the DFT, the k plus nth coefficient of this DFT, if I want, see, we know that DFT is given by this formula, xk equals to n is equals to 0 to n minus 1 x of n e to the power of minus j 2 pi k n by n. Now, just as you used to do, you are changing the value of this. So we are writing that if k plus nth coefficient, if I want k plus nth coefficient of DFT, then it's going to become x of k plus n. So what will be the change in the formula here? N equals to 0 to n minus 1 is remaining same. This is n. This is not going to change. The place wherever there is k, that will be replaced by k plus capital N. So xn e to the power minus j 2 pi, small n write it, capital N write it, and this is k plus n. Now separate this e to the power thing. This is going to be n is equals to 0 to n minus 1, x of n e to the power minus j 2 pi n into k by n into e to the power minus j 2 pi small n capital N by capital N. Now this value, the mod value of this one, for any integer n, this is going to be 1. For any integer 1, for any integer n, it's going to be equal to 1. So this finally reduces to the same thing. N equals to 0 to n minus 1 x n e to the power minus j 2 pi small n small k by capital N. So this is what? This is xk only. That's why xk plus n becomes equals to xk. What was the thing here? You had to write it separately. So remember, writing it separately will make the proof for it. Let's go for the third one. That is the circular time shift. What is meant by circular time shift? You have already seen time shifting. So what does it mean by circular time shift? So basically the circular time shift, there are two types. One is the right circular shift and the other one is the left circular shift. So when we are saying circular time shift, that means one point is fixed. You are fixing some point, you are fixing the length and then you are shifting it. So suppose I have a value, say I have a value 1, 0, 1, 1, 0. Okay. Now I want to right shift it. Okay. So two types of shifting is there. So what I will do is when we are doing the right shift, we will put out the last one. The last one over here, we will put it out and put it in the first place. So it becomes 0, 1, 0, 1, 1. If same value you were doing left shift, let's do this side, 1, 0, 1, 1, 0. So you will take out the first value and put it at the last. So it will become 0, 1, 1, 0, 1. This is left shift. In case of right shift, pull out the last value and put it in the first. Put out the first value and put it at the last. So basically, it is not, the length is not going to increase. It is fixed. So pivoting from this point only, it is going to change. Whether it is 1, 2, whatever it is. From here only, it is going to circularly change. It will go towards the first or the last. Here also same thing. That is why it is called circular time shift. Now the how to do the proving for this? What is the statement of this? Let us first see that. So for that it is written as, if the DFT of same thing, if the DFT of xn is given as xk, then the DFT of xn minus m modulo n. Why this modulo n? Because you are fixing it, the length is getting fixed. It will not extend in time. So that is why that is written as modulo n. Okay, that is going to be x of k e to the power minus j 2 pi k m by n. Everything is remaining same. See, here you are shifting in time. Here it is multiplied by the frequency, right? So same thing which was happening in case of Z transform. Here, just you have to keep in mind that since the length is fixed, so we have to put here modulo n, finite, right? In DTFT also same thing is happening, but the thing is that it was not fixed, infinite length. Now proof. So proof, we will always start with this part. So write it here. DFT of x of n minus m. This is small m. Means you are shifting it m units modulo n. So write the formula for DFT. That is going to be small n equals to 0 to capital N minus 1. Xn minus m modulo n e to the power minus j 2 pi k n by n. Now here what you need to do is this n minus 1, let n minus m is equal to p. Okay. Now if n minus m is equal to p, in the place of n, small n, you can write it m plus p. So let us rewrite this part. That is n equals to 0 to n minus 1 xn minus m. So n minus m, what we have taken it? P. So I will directly write here p. xp e to the power minus j 2 pi k. Now here I will write m plus p divided by n. I'll rewrite it. So previously here it was x n minus m modulo n. So what we are going to do is we are writing here xp. N is equals to 0 to n minus 1. xp modulo is n. E to the power minus j 2 pi k by capital N, and this is m plus p. Now break it. Same as you did in the periodicity property. So what it will become? X p e to the power minus j 2 pi k m by n into e to the power minus j 2 pi k p by n. Right? Till here, everything is like the previous portions only. Just you have to keep in mind that you have to take the previous thing, that was n minus m, you are taking equal to p. So once you take that n minus m is equal to p, the rest of the things will go on normally. Now see, Just change the positions. Okay, here I have missed this n is equals to 0 to n minus 1. Let me write it. N is equals to 0 to n minus 1. Now, if I put this part inside and this part outside, then it becomes n is equals to 0 to n minus 1. For the time being, I'm writing here xp. This part I'm putting inside. So e to the power minus j2 pi k p by n together. And this one as e to the power minus j2 pi k m by capital N. So here what is changing? Small n was changing and there was no small n over here. Or actually here when you are writing, when you are taking p, sorry, this part here it is going to be p now. It is going to be p. This portion you have started with p. So the moment you change this to p, change here also to p. So there is no p in this portion. That's why we kept it out of the bracket. Now this full thing is basically what? This full thing is the Fourier transform. So that is xk and this is e to the power minus j2 pi k m by n. So this is proved. Once again, let's do this very quickly. What was it that we have to do the circular time shift? Circular time shifting means that you have to shift with n units around capital N. So same as Z transform and DTFT and all, xk into e to the power, it is going to be multiplied with e to the power something and where the shifting will be of m, right? So the next thing that we did was we took the LHS of the equation. We wrote the formula of DFT, which is e to the power minus j2 pi k n by n. Now we took n minus m is equal to p. When we took n minus m is equal to p, this full thing n minus m will be written as only p. And this n over here, the small n, this is written as m plus p. So this you wrote as m plus p. Also the summation limits will change from p is equals to 0 to n minus 1. So because here n minus m you have to change to p, so this limit is going to change. Now you are going to break this into two e to the power minus things. So here this is e to the power minus j2 pi k m by n and this one will be e to the power minus j2 pi k p by n. Now here only it is p and this one is p. So those two you were bringing together, that is becoming xk and outside this part is there. This way we have proved three properties. In the next class, we are doing other three properties, or if it will be not too long, then I will complete all the properties in the next class itself. Thank you, everyone.